Alrighty, as far as I know, we are live and recording, and we even have audio this week. So, Friday, we had webcam issues and document cam issues, and I tried to fix that, and I warned you that the universe might collapse on itself, and it didn't do that, but we did lose audio in the process. So, hopefully things are working. All right. Hope everybody had a good weekend. We are now in week 6, so officially past the halfway point. And I want to talk a little about the midterm exam and get some things out of the way with that. But any questions before we get into that kind of thing? Any questions on TA3, stacks, queues, hashes, or what we started talking about with trees? It's a quiet room. Well, there's 11 people in there. Maybe that's part of why it's quiet. I've been up since 4:30 this morning, so I'm kind of buzzed at the moment from sleepiness. So I'll try not to talk too fast. All right, let's start with the midterm. So I posted a placeholder for the midterm, and I sent an announcement last night, and the announcement mentioned two things. So first of all, my office hours tomorrow start at 9 instead of 8:45. I have a computer science meeting to go to that runs from 8 to 9. So I'll be in office hours 15 minutes later than usual. The other part of the announcement was about the midterm. So the midterm is on Friday. Your midterm will start at 10 o'clock and goes until 10:55. And it's set up as a Canvas quiz. Not a Canvas quiz, it's set up as a Canvas assignment. So the assignment will open at 10, and you'll be able to download a PDF, and the PDF is the midterm exam. And you have to upload your answers as a PDF by the deadline. If you don't know how to do this, if you haven't already done this and can't do it in your sleep, you need to figure out how to do this before Friday. Okay? Don't start your exam and then at 10:48 try to figure out how to upload it as a PDF, right? Do this ahead of time. Make sure you know how to upload, how to export your answers as a PDF, and how to upload that. Your answers need to be typed, right? And you're not editing a PDF, that's correct. And you're not doing a Canvas quiz, and you're not doing an essay upload, okay? You're typing up your answers in whatever editor you choose, and then saving that as a PDF and uploading that PDF to Canvas, just like you would a homework in 215, for example. So make sure you've got the nuts and bolts of that down. And let me see what else I mentioned in there. Canvas is fast today. Alright, so yeah, your upload must be typed. Upload is a single PDF file containing your answers. Please don't upload 5 different PDF files, one per page or something like that. Figure out how to export. If you're using Word, if you're using OpenOffice or LibreOffice, if you're using Google Docs, right, all of these will export PDF files. But figure out how to do that ahead of time. I'm giving you 55 minutes for the exam. I'm going to penalize you 5 points per minute after that. Okay, the exam is not going to close because I don't want people emailing me late submissions saying I missed the submission deadline, here's an email, right? So submit through Canvas, but whatever Canvas says, if it says it was 3 minutes late, that's going to be 15 points. So you got to get it turned in on time, okay? And I want you to log into Zoom during the exam so that if there's clarifications that need to be made, if there's typos or things like that, I'll talk about them in the chat window. Okay, and then I'll let you know when it's 10:50 and you got 5 minutes left, and make sure you turn stuff in. Is there a way to use VI and export it as a PDF? Do you have OpenOffice, which is like the open source version of Microsoft Word? So you can edit your stuff in VI and then just copy and paste it. Use a fixed spacing font and then export as a PDF. That's a nut you need to crack sooner or later anyway for lab reports and things like that. But yeah, you can write in your favorite editor and then paste it into a Word document or an OpenOffice document. Don't ever try to write code inside one of these word processors because it's not a fun experience. In an ideal world, I'd have you submit your answers through Git, but I'm not going to do that. Can we ask what will be on the midterm? There'll be some programming questions. There'll be some short answer, fill in the blank, multiple choice questions. And it's basically everything that we've done up through this point, not including trees, which we started on Friday. So no trees, but you'll see, you know, structures and pointers and malloc and linked lists and queues and stacks and hashes. All right, so there's an honor statement in the beginning of the midterm, and you'll need to read that, and then at the top of your answers that you submit, you're going to type the word honor statement and then type your name next to it to indicate that you agree to it. And the gist of the honor statement is you have to do the work on your own. You're not allowed to consult with anybody. You're not allowed to ask anybody for help except for me. Okay, you can pop into chat and send me a message and so on. But everything else you've got to do on your own. You're not allowed to ask for help from anybody else or give help to anybody else. You're not allowed to use a compiler, okay? You're going to be writing code. You might be writing it inside VI. You're not allowed to GCC it, okay? This is an honor thing. You can look at old code if it's yours, or if it's in your notes, you can look at the textbook. But you are not allowed to Google. You're not allowed to you know, go to Chegg or things like that. All right, yeah, 55-minute exam starts at 10 o'clock, ends at 10:55. 5 points per minute for late submissions. All right, so you're not allowed to use a compiler. You're not allowed to use any sort of syntax checking or syntax completing editor. If you use an editor with syntax highlighting, that's okay. Okay, because I know some people do that. I'm not going to make you turn off syntax highlighting. But don't use an IDE, don't use Visual Studio, don't use IntelliJ, don't use Eclipse, don't use anything that completes your syntax for you or tells you, you know, you're missing a bracket here or things like that, right? So pretend you're writing this out by hand, but I want you to be able to type it. All right, and like I said, there's going to be some programming questions, which will be related to structures and lists and mallocs and stacks and queues and hashes and things like that, and then some short answer questions. All right, any other questions about that? All right, well, let's continue with trees. So how much percent is the midterm? I don't remember off the top of my head. Check Canvas. It's probably like, oh, I got Canvas here. I can check. It's probably 20-some percent. But let me see. Looks like the midterm is 20%. Yeah, please do not miss your midterm. Okay, and again, it's taken during class. It's not something you just take sometime during the day. It's regular class time. It is possible to pass without taking the midterm. Yeah, or the final, but not both. If you don't want an A. All right, let's talk more about binary search trees. So we started talking about these on Friday, right? And these are really the central object of the next part of the course, and in some ways I would say kind of the central object of data structures to a larger degree. There's a lot of different variations on trees, but once we've gone through trees and we've done some of the things we're going to do with them, I think we'll be at a different level as far as comfort with data structures. Linked list was a full-on data structure where we were dynamically allocating things from memory and so on, and you're using them now, you know, for stacks and queues. Trees are an additional layer of complexity. The algorithms get much more complex. And so once we're through this, right, it may be a bit of a push to get there, but once we get to the other side, we're going to be in really good shape as far as, you know, we understand data structures and we can work with them. And then new structures are just, you know, it's like new languages. It's just different specifics, but the same general types of things. All right, so binary search trees, right, had characteristics of a binary tree with the additional property that everything to the left of a node had to be smaller and everything to the right of a node had to be bigger. So this is a valid binary search tree. And I could add some additional nodes here. Maybe I could put a 20 down here and a 75. And I could put a 65 and a 55 and a 52. And this is still a binary search tree. Now I know that because I can pick any node in this tree. Let's look at this node. And I can say, is everything to the left of it smaller? Yes, it is. And in that thing to the left, does that property also hold? In this little subtree, if I pick any node, is everything to the left of that node smaller and everything to the right larger? And that does satisfy it. Now, where things stop to work that way is, you know, if I do something like that, it's no longer a binary search tree. Because, you know, everything's fine until I get down to this point. At this point, is everything to the right smaller? No, it's not. I mean, is everything to the right bigger? It's not. Alright, but this is a good BST. And so is this, and so on. Alright, so we've got a binary search tree. Don't worry about where it comes from yet. We'll talk about building it in a minute, but it's a little harder to build than it is to use. So let's talk about searching. And we went through this on Friday, right? If you want to search for 400, You start at the root. You always start at the root. It's like the sentinel node of a linked list that you always start at. Always start at the root. 400 is bigger, so move to the right. Here's the root of a smaller tree. The root is 200. 400 is bigger, so move to the right. This is also a tree. The root is 500. 400 is smaller, so move to the left. Well, this is also a tree. It's a tree with one node. The root is 300. 400 is bigger, so it would have to be to the right of that node. And there's nothing to the right, so we can say 400 is not in this tree. If we search for a 65, smaller than 100, so we go left. Bigger than 50, so we go right. Smaller than 75, so we go left. There it is. So that's in the tree. All right, got the idea of how we search? Awesome. So let's write some pseudocode. And we're still not going in the language of C yet. I'm not going to actually make a struct node and do that kind of thing. I want to stay one level above that. So pseudocode. So we want to search for a number in a tree, and we're going to pass the search routine the root of the tree. And so it works like this. Then you can imagine there's a data piece and a left piece and a right piece for this root. Maybe I'll draw a structure, I don't know. If the root's data is equal to the number, then we're done. If the root's data is bigger than the number we're looking for a 65, and the root's data is 100, which is bigger, what do we want to do? Branch left or low. So we want to move down to this spot, so I could do something like this. Set the root equal to root right, and go back up and try again. Alright, so root is equal to 100. Root's data is 100. The number we're looking for is 65. 100 is bigger than 65, so we're going to change root to be whatever's on the left. So we'll change root to here. If the root's data is less than your number, then we go to the right. So 50 is smaller than 65, so we'll change root to be the thing on the right. And then we'll come up here again. Root's data is bigger than the number, so we'll change root to be the thing on the left. And now when we check root data to see if it's equal to number, it is, we'll say success. So what's the other option? What happens if the number is not in the tree? What's this algorithm going to do? It should kick out of the loop. It's not going to. It's actually going to segfault. But we'd like it to kick out of the loop. So, say we're looking for 400. So root, root, root. Root's going to come down here. So we're doing 400 again. There's the root. And root data is less than our number, so this is going to say root equals root arrow right. Well, remember these leaf nodes, that's going to set the root to null. So it turns out a really easy way to terminate this is if root equals null, then it's not found. And this also works in the case where you're trying to search an empty tree. Because remember, for an empty tree, root is null. So if I say search this empty tree for some number, my very first check is going to say, hey, root's null, number's not found. If root is not null, I'm allowed to check the data, to check the left, and to check the right. So none of this will seg fault. But it may change root to be null, so that the next time through, I'll kick out of my loop. Perfect world with no seg faults where you can access whatever memory we wished without consequence. That would be a good song lyric, like a spoken section in the middle of some like cool guitar riff or something. And like a few people would know what you were talking about, and that would be awesome. So do you need to set up the whole tree again if you add or remove a number? Or we're going to talk about adding, we're going to talk about removing. No, you don't have to set it up from scratch. We'll find a really simple way to add things, and then later on we'll talk about a really confusing way to delete things. But it's an awesome delete algorithm. But let's finish up search first. All right, so I am going to give you a bit of a structure here, because even though I'm writing pseudocode, of course it looks like C. So let's look at what a root node would look like. So let me call this a struct tree node, just so we don't confuse it with a linked list node. So I don't know, let's do an integer data and a struct t node left and a struct t node right. So that's fine for the nodes of our tree, right? And they look, you know, just like a linked list node. If we call this next, that would be a linked list, but we've got a second pointer in there. And remember, they don't point to the following node, they point to the middle of the left and right subtrees or sublists. So we've got two of those. But, you know, kind of what you'd expect from what we've written here. All right, so search is really just, you know, start here and bounce down until you either find a node, or you say, you know, it should be on this side of where I am, but there's nothing on that side. And that's when the new root that you're moving to turns out to be null. And I'm assuming here that, like, you know, root's just a temporary variable, so I can change it and I don't actually change the root. All right, got the basic idea for search? If so, we'll go on to add. All right, here's where it starts to get real. So this was our binary search tree. And I don't know, somebody give me a number. First person to give me a number wins. 25, awesome. Okay, so let's add 25. So where could I add that 25 without changing anything else in this tree that would still make this thing a binary search tree? to the right of the 20. And I think that's actually the only spot that you could add a 25 without breaking the binary search tree-ness of this. Right? Because if I put it down here, or here, or here, or here, I'm in trouble because 25 is smaller than 50, so it can't go on any of those. Can't go on anything over here because it's smaller than 100. Can't go to the left of the 20 because it's bigger, so it's really, really got to go in exactly one place, which is right here. If I do it to the left of 52, that's fine for this subtree, but remember, everything to the right of 50 has to be smaller than 50. And if I hang it off here, that's technically to the right of 50. So when we think about right or left, we have to think of like entire subtrees. Like everything here is to the right of 50. Everything here is to the right of 100. And all of this stuff is to the left of 100. All right, now how did you know to put it right here? How'd you find the magic spot? Saw 20 and said that that was smaller, less than 100, less than 50, greater than 20. Ah, okay. So I think we got an algorithm here. We can do exactly the same thing that we do when we search for something. Remember, if we were searching for a 25, we would go left, left, right, but then we'd discover there's nothing to the right, at which point we would say, hey, it's not in the tree. Well, if we want to insert it, let's just put it in at that spot where we would normally give up our search. And that turns out to be the algorithm for inserting. So so somebody else said 15. Let's add a 15. So smaller, go to the left, smaller, go to the left, smaller, go to the left. There's nothing to the left. That's where the 15 goes. All right, so someone asked about 60. So compare it to 100, it's smaller, so move left. Bigger than 50, so move right. Smaller than that root, move left. Smaller than that root, move left. Bigger than 55, move right. There's nothing available to the right. That's where the 60 goes. Still a binary search tree. Yeah, it's pretty slick. And this is guaranteed to maintain the property that this is a binary search tree. In an algorithms course, you would actually prove that, but we can kind of see it's true. That's where you say it's clear. All right, so let's jot down some pseudocode. And I'm going to assume the number is not in the tree, otherwise you have to deal with some special cases. So so if our number is less than the root data, then if there's something to the left, we want to move down there and keep going. But if there's nothing to the left, right, if root left is null, then set the root left to your new node. So, you know, make a new node. So make a node where left and right are null and the data is equal to your number. And now we're going to move down, we're going to find where to insert it. So if your number should go to the left of the root, see if there's anything to the left. If not, set the left child equal to that new node, and we're done. Right? Otherwise, move to the left. Go back up. And then just be symmetric on the other side. And if we know our number is not in the tree, we don't really need this if statement, because if the number is not smaller than the root and it can't be equal to it, we know it's bigger than the root. But I'll put an if there anyway. So we're going to move to the right, unless the right child is missing, in which case set the right child equal to your new node, and you're done. If there is a right child, move there. And then go back up to the top. So yeah, we don't shift anything around yet for inserting a node. We will eventually. All right, does this make sense so far? So all we're doing is what we did here. Let's add 80. So 80 is smaller than the root node. The root left is not null, so we change the root to here. 80 is bigger than the root node's data. The root node's right is not null, so we set root equal to root right. 80 is bigger than the root node's data. The root node's right pointer is null, so we change the right pointer to be this new node that we created in the beginning, and that's where the 80 goes. That works great on paper. There's one slightly horrifying detail. Suppose we start with an empty tree. Suppose we say something like, root equals null, and then we say insert root comma, whatever we want the root of our tree to be. Well, I'm going to make a new node with that root value, and the first thing I'm going to do is compare that number to root data, and I'm going to segfault. That's the slightly horrifying part. Actually, it's not. It gets worse. All right, I'm going to segfault if root is null. So we have an edge case. This is an edge case that we avoided by having a sentinel node in our linked lists. We can't avoid that anymore. So the edge case is where the root is null. We're going to create a new node. We should simply return that new node. That new node should become the root. So here's the edge case. If the initial root is null, then the new node should be the new root. It gets worse because we have no way to change the root. The root is being passed to us by value. even though it's going to be a pointer to a struct node, we can't change the value of that pointer. We can change the thing that it points to, but we can't actually change that pointer itself, because C is always passed by value. So if we were to actually write this in C, this would be, struct T node star root, right? But changing the value of root in here doesn't change root in the program that called us. And if we wanted that to change, we would have to pass the address of this struct node star, and this would become a struct node star star root, and now we've just ruined our beautiful Monday, right? So we're not going to do that. Instead, what we're going to see with most of these routines is we're going to write them to return a root of the tree. So here's what we would do. We'd write our function like this. It would be a function called insert that takes a root, which is a pointer to a T node, and it takes a number to insert, which is just an integer. But the function itself also returns a pointer to a T node. And when we call it, we're going to call it like this. We're going to call the insert function, pass it. Let me go ahead and set this up. So root will be a pointer to a struct T node. We'll go ahead and we'll call insert. We'll pass it that root. We'll pass it the value to insert. But we're always going to say set root equal to the return value from this insert function. Alright, so what can we do in here? We'll make a temporary now, because we're going to return root at the end, and in general we don't want to change the root. So we'll use a temporary pointer, which is equal to the root that we're passed. So make a new node. Or whatever. So I'm supposing I've written a new T-node function that I can give a number to, and it'll create a nice node for me that's of type struct T-node, and the left and right children are null, and the data value is equal to num. So I'm just modularizing code here. So this is just, making a, let me call this new. Just making my new node called new. All right. So if temp is equal to null, if the root that I was passed was null, I'm just going to return this new node, and my main program is going to make that new node the root of the tree. So this is how I go from a totally empty tree to a tree with one node. Alright, so I'm going to write my insert function, start off by making your new node, so call malloc and set the data value and all that stuff, and then see if the root of the tree that you were passed was empty. And if it is, we're not going to do anything else except just return that new node as the root of the tree. Otherwise, the tree is not empty, so move temp, go left and right, Find the leaf you want to hang yourself off of. Add new to proper spot, and then just return the original root back. What was dark? Hanging your node off of. You can't actually hang yourself from this tree anyway because it's upside down, right? So you'd just be like floating. Yeah, so do your loop that we were doing here. Move left and right, work your way down to a leaf node, figure out where you want to attach that new node to, set the left or right child equal to that new node, and then return the original root, right? And so most of the times when I call insert, whatever I pass as the root, that's what I'm going to get back. This whole mechanism is here for one case only, and that's the case where we're changing the root, and that only happens when we're going from an empty tree to a tree with one node. Right? In other words, when we're going from totally empty to a tree that looks like that. Alright, that's the end of the slightly horrifying part. Slightly horrifying because we're going to do this with pretty much every function we write from here on out. When we delete, when we insert, when we initialize, and so on and so forth. Search, we don't have to do that because we're not modifying anything. All right, questions on this? This is probably a little fuzzy at this point. We'll do some code in C tomorrow to start to clarify this a little more. But for a first pass through this, any questions on it? Yeah, code always helps. Well, since we only have about 4 minutes left, instead of starting some code on that, let's look at the next question. Which is traversal. Printing a tree, for example. Suppose we have this tree. Remember, the only thing we have for a tree is the root. We've got a pointer to this first node. We can get to every other node because trees are connected. We can get to this node by taking this and following the left child, the right child, the right child. Hey, there's our 80. So it's all accessible from this one point. And that's the only point from which everything is accessible. If we only had a pointer to this 50, there'd be no way to get to any of this stuff. Because our pointers just go down, right? Left subchild, right subchild. But from the root, we can get to everything. But suppose you want to somehow visit every node in this tree, what we call traversal. You want to go through all of the data in here and say print out the data values. And it's a little tricky to think about. Because we can print the root value pretty easily, just print root arrow data, right? And we could print, root arrow left arrow data and root arrow right arrow data and take care of those two pieces. So we've got, a few nodes printed. But to print these nodes, well, this is root left left, this is root left right, this is root right right, root right left doesn't exist. And the further down we go, the more things we find. So we need some kind of loop that's going to let us see everything in the tree and not get lost. And you and I, if we wanted to print the values of this tree, probably the most natural way is just say, 100, 50, 200, 20, 75, 500, 15, 25, just kind of go across each row. And that works well for us because these things are laid out on paper and there's a distance from the top that's uniform. But you know, that's not how these things sit in memory. In memory, who knows? It's just a bunch of data pointing to other locations. So I'll show you the hard way, and we'll start making this easier tomorrow and Wednesday. Here's the hard but efficient way. Start with the 100, okay, and put a marker there so that we can come back to it, okay. Here's a 50. I'm going to print that out, and I'm going to put a marker right there. And I'm going to go to the left, and I'm going to print out the 20. I'm going to put a marker there. And I'm going to go to the left, and I'm going to print out the 15. And there's no children off of that. So I'm done with that part of the tree. I'm going to go back to the last marker that I had, which was a 20. And now I'm going to look to the right. And there's a 25. And there's no children off of that, so that's done. Alright, and I can go back to the marker, and now I'm done with this whole little subtree. So I'll go back to the last marker I put down before that. That was right here. And I'm going to say, okay, now I've got to go to the right. So I'm going to look at this tree, and I'm going to do the same thing. I'm going to search 75, right, print that out. And now I'm going to put, you know, some kind of marker on that. And come over here, and there's a 65. And I'm going to put a little marker there. And come over here, and there's a 55. And I'll put a marker there. And come over to the 52, and there's no children, so that's done. And then come back to my last marker and go to the right, print out the 60, there's no children, so that's done. Come back, and I'm done with that marker, and I'll go to the previous marker, and there's nothing to the right, so I'm done. And go back to the previous marker, and go to the right, and do the 80, and there's no children, so that's done. And so I'm done with this marker, and I'm done with this marker, and guess what? I've just done half my tree. Now I got to go back to the last marker that I had, and I got to go over to the right and do the same thing. So what's the data structure that we're exploiting here? Someone said depth first search, which is absolutely right. What are we doing here? We're putting things down to hold our place, and then we're going back to the last thing that we put down. And we're not going to the first thing that we put down until we're done with everything else that we put down after that. So what's the 4-letter acronym here? Be polite. You got a 50% chance if you guess. Almost. Actually, it's a LIFO. It's last in, first out. Right? Or first in, last out. So the first marker I put down, that was the last one to be removed. Right? So I did this, and I did this, and I did this, and eventually did this. And then the first one I put down, that's the last one to come out. So yeah, that is a LIFO. Which means we can do what we just described with a stack. And so tomorrow I want to write some C code to do this insert business, and then I want to look at using a stack to do this tree traversal. And we'll look at different versions of tree traversal, and we're ramping our way up to good stuff. We're working our way up to recursive algorithms. All right, cool. I will leave you with that. I will see you next time. Thanks.